Hi. What we have been doing up to now was related to S-domain. So we are doing analysis in S-domain. The first frame we examined what happens to Kirchhoff current law and voltage law equations in S-domain and what would be the definition relations of the elements in S-domain. So we have examined this in here. And then we said how we can get benefit get benefit for the analysis of S-domain using the serial parallel connections, and how we can use the source transformation in S-domain analysis. We examined this in this frame, and then we examined the general analysis techniques. What we mean by saying the general analysis techniques is to find out all the elements, current and voltages for the given circuit. In these special techniques, we will be calculating only one of the element, current and voltage only. Therefore, this is special technique and that's general technique. So we will be examining these special techniques in this video. In between, we examined the natural and force solutions. Why we examined those? Because in S-domain we said we can calculate these solutions and then transfer it to time domain solution, but we cannot do that in frequency domain. That is one of the advantage of S-domain, so we examined this already as well. So that is the subject now we will be examining in this video. So we are going to mention the Thevenin-Norton equivalent circuits in order to find out one of the element current within a circuit, current or voltage, say. We are going to examine this on an example circuit. That's our example circuit. That is our load, you might call it, or this is a load impedance, you might call it. And we are going to calculate this load impedance, current and voltage only, not the other elements, current and voltages. These blue area elements, current and voltages will not be calculated by this, cannot be calculated by this method. You've got to use general analysis techniques if you want to do so. So at the end, as you see here, we are going to find out VTH, what VTH, Thevenin voltage circuit is, and what ZTH is, so that impedance is. If you know this VTH and ZTH, then IL, which is the current of this load, so if you put that load here in this circuit, you can calculate the load current as a formula like that. So what is the advantage of this? We said if you change your load for any load, this formula stays as it is. That means you are not going to recalculate Thevenin-Norton and Thevenin-Norton voltage and impedances in here. That is the advantage. Now let's go in how we are going to find out VTH and ZTH in this example. So we've got to come out of here and escape. And move to open board. In the open board, that is the circuit that we are dealing with. What we're going to calculate VTH, that's one of them, and ZTH. Let's calculate VTH first. VTH calculation. VTH is the voltage between these terminals V, A and B when this is removed or made open circuit. So remove it or open circuit means that current is equal to 0, isn't it? So when this current is 0, you got a voltage here. That voltage is VTH. So that means open voltage of A and B is equal VTH. So that means I'm going to calculate that VAB. That VAB is going to VTH when these AB terminals are open circuit. So open circuit means that current is equal to 0. What does this mean? So that current is the summation. So let's choose references for these two. So that current here is the summation of those two currents. So if we write the Kirchhoff current law equation for this node, summation of those two current is equal also this resistor current. We already said summation of these two currents are equal to 0, so that current is going to be 0. So that current is 0 means that voltage, by definition relation of the resistor, that voltage is also equal to 0. If that voltage is 0, then this voltage becomes equal to that dependent source control voltage, isn't it? So Vx is equal Vs. So we simplify the circuit in order for the calculation of that VAB here. So I can write now, so that current is 0, so that current 0 and that current 0. So what I am looking for, that open circuit here. The open circuit voltage is, if that voltage is 0, if I wrote a Kirchhoff voltage law equation for this loop here, it's going to be Vs minus Vs plus Vc, that capacitor voltage, plus VAB is equal to 0, isn't it? So from this, VAB is equal to Vs minus Vc. So Vs is the source, isn't it? So source is known, so I am going to keep it as it is. What I am going to calculate is the capacitor voltage. If I can calculate the capacitor voltage in terms of Vs, that means I can find that VAB. So how I'm going to calculate this capacitor voltage here? If you write Kirchhoff, so there is no current here, no current here. So in this loop there is no current, but in this loop there is a current. How that current came in? Since Vx is equal Vs, so that means this dependent voltage source voltage is equal 0.Vx. That means 0.2 Vs, isn't it? So this becomes a source. This source delivers a current to that loop, isn't it? So let me to write now Kirchhoff voltage law equation for this loop. So loop direction, assume that loop direction is like that. So plus Vc minus VR, this resistor voltage. Let's say, make it 1 ohm, maybe it is easier to see. 1 ohm plus 0.2 Vs is equal to 0. So in here, if I write now 1 over SC IC minus 1 ohm I 1 ohm, 0.2 Vs is equal to 0. Now look at that AC, IC and IR current. Since this current is equal to 0, these current values are going to be the same apart from the sign, isn't it? So that means now I'm going to write here 1 over SC, sorry, that's plus 10. Minus R is going to be equal that IC, since this current is 0. Both of them coming towards the road, towards the node. So if I write it, IC plus I 1 ohm is equal to 0, isn't it? So more proper way of writing is this. Then I 1 ohm is equal minus IC, isn't it? So this is what I have done. I am going to do it here. So I was going to plus 1 ohm IC is equal 0.2 Vs minus right hand side, if I put it on the right hand side. Now look at that IC here. Definition relation Vs 1 over AC IC, then IC is SC Vs, isn't it? So SCVS 1 plus 1 over SC SCVS is equal minus the focal point Vs. So I made a mistake, isn't it? Not Vs, that's capacitor voltage. So I am correcting myself now, saying that is Vc and Vc. Definition relation of the capacitor. So I replace this, so that is also Vc. So as I said, I am trying to find out Vc in terms of Vs. Why is that? If I transfer that Vc here to Vs, I can calculate that VAB. Now this is minus Vs, so minus Vs from this, you can say minus Vs, so that's going to be minus. If you multiply both sides minus, you get minus Vs here is equal 0.2 over 1 plus 1 over SC. C is equal, given here, 0.5 farad, isn't it? So that C here is 0.5 farad. So we calculated minus Vc. If I put that minus Vc here, this move to here is going to be Vs minus Vc replaced with this plus 0.2 over 1 over S 1 over 2. So that's Vs, isn't it? Since this is Vs, there's a Vs here, so put a Vs here. So if you look at this equation now, so that is not good, that is S, not 5, comes from the IS. So we've got VAB is equal something multiplied with Vs. So if you do this, you're going to end up with this. So VTH is VAB. So you can end up with this. I don't want to write it once more. So it is just a basic for operations that you know from primary school. Okay. So the next step to do is to find out impedance seen between these two terminals. There are two ways of calculating this impedance here. One way is you can make these two terminals short circuit and calculate this short circuit current. VTH over short circuit gives you the impedance that you see from here. That's one method. In here I will be using the second method. In the second method, what I am going to do is this. I am going to remove the independent sources within the given circuit and apply a test circuit to these terminals and find the test circuit independent voltage source current delivered to the circuit. So I am going to repeat what I said here. Move this side a bit and this one somewhere here, just a while. Now I am writing what I said here. I'm going to draw here. So when you short circuit this, that means this resistor, that terminal is going to come to this. So it's going to be like that. A resistor and a dependent source, dependent voltage source 0.2 Vx, and a resistor, 1 ohm resistor, this 5 ohm resistor, and there is a capacitor here. Now I am saying I am going to apply between the terminals A and B a test voltage Vt and find out that It, which is delivered by this independent source, It current. So ZTH, Thevenin impedance, is equal Vt over It. You could see it here. If you make the independent sources in your circuit deactivated, this is going to be short circuit. If you apply a Vt here, terminals A and B, independent voltage source Vt, that voltage source over that It current is going to be equal to that ZTH. So that is the rule of calculation of ZTH. So my aim now in this circuit, calculate this It current in terms of Vt. So this is our capacitor current, that is resistor current, and that is this current. Now this voltage here is equal Vx, isn't it? So if I write Kirchhoff current law for this node, it's going to be towards It is equal minus Ic minus I1 ohm. So if I can calculate that Ic and Ir in terms of Vt, then I would be able to calculate that. So It is equal, what is the current of the capacitor? So consider now, this is node voltage here, if that's ground. So node voltage is Vx, isn't it? Vx, this node voltage is equal to Vt. Vx minus Vt over this impedance gives you the current of this impedance. That means capacitor, isn't it? What I am saying is that Vx minus Vt over 1 over Sc, that's impedance of this impedance, gives me that current, so that IC. So what I am saying is this, make it red. This current is this current. So it says minus now, current of the resistor. So looking for this resistor current now. Resistor current, so what is the node voltage first? Consider this node voltage. I made a mistake, isn't it? So the sign here, positive sign on the right hand side, negative sign on the left hand side, which is the opposite. So I correct my mistake now. So plus here, minus here. So this node voltage is equal to what? That is the voltage, 0.2 Vx. That is Vx. So between this node and this node, this voltage is Vx, 0.2 Vx. That means 1.2 Vx, isn't it? So this is this node voltage. Node voltage 1.2 Vx. So minus this node voltage is equal Vt. So that means now Vt, once again, 1.2 Vx. That is this node voltage minus this node voltage minus Vt over 1 ohm gives me this current. So that's that current. So let me show it to you in a green. So what I am saying, this current here is this current, and this current is equal to this one in terms of node voltages. So what we have done all that, we transferred now, we are trying to calculate IT in terms of Vt. So this Vt is okay, that Vt is okay, IT is okay. I would like to get rid of from that Vx. How I am going to get rid of from that Vx is easy. Let's consider this node. So we said this IT current, the negative form of it, is the summation of those two, isn't it? Summation of those two is equal to that, isn't it? So this current here is equal to IT. If you consider the direction as well, this current is divided into and then end up with here. So I am saying it by using the Kirchhoff law equations, not the current is divided by one or two groups, two branches, but by using the Kirchhoff current law equations, that I am saying this current is equal to this one. So that means now this is equal to IT. Well, that's a good conclusion, saying that Vx then is equal 5 times IT. So if you replace that Vx with 5 IT, so that means you found your equation. IT is equal minus, now Vx 5 IT minus Vt over 1 over S 1 over 2 minus 1 over Vx multiplied 5 Vt minus Vt over 1. So if you do the calculation here, you're going to end up with here, here are ZTH. So I'm talking about, if you do this calculation here, you're going to have ZTH is equal VT over IT, and this is equal to this 5S plus 14 S plus 2. So we calculate ZTH here and VTH here. Then we are saying now, if you look at this circuit here, and if you if you put this load here, that resistor plus an inductor. So resistor is 2 ohm, inductor 1 Henry. So this impedance here, which is load, 2 times SL. L is equal to 1 Henry. So it's going to be S plus 2. So this is the load impedance. So this voltage divided the serially connected impedance's equivalent impedance, which is IL, is VTH over ZTH plus ZL. Isn't it? What I am saying this, that is ZTH impedance that we have already found, and that is load impedance, that's this one. Why I add those two impedances? Because they are connected in serial. So this is the equivalent impedance. VTH over equivalent impedance give me that current. So that current is also the current of the load, isn't it? Because of this node. So that is IL. So that IL. So if you look at that formula here, we've got VTH Thevenin voltage, this is ZTH Thevenin impedance. Any ZL impedance I put between the terminals A and B gives me that current. So we could use that formula for different impedances, load impedances, just by replacing that load impedance in here, keeping the VTH and ZTH as it is. So if you don't use these analysis, for different loads that you connected to the terminals A and B, you've got to calculate, analyze the whole circuit for each load. In here, for each load, I will be using the same formula here, apart from ZL. VTH and ZTH calculation will not be repeated. That is the advantage of this method, of course. So let's come to the superposition application in circuit analysis. In here you see a S-domain circuit, a circuit given in S-domain, and the inductor and capacitor has got initial values rho and gamma respectively. So we already seen that these elements, capacitor and voltage elements, equivalent circuits in S-domain includes the initial condition in it. So let me different color. So this L here is the replacement of this L here, which includes that rho in it. So that's independent current source. Current value is rho over S. And similarly, this capacitor S-domain definition relation is this. Make it different color. So that capacitor has been replaced with these two elements in S-domain. you might not remember those, but if you go to the beginning of the S-domain analysis, you're going to see these equivalent circuits. So after that transformation, the time domain given circuit to the S-domain, in this S-domain I have got altogether 4 independent sources. 4 independent sources. So superposition theorem tells me if you've got more than one independent source in your circuit, calculate the element current and voltages for each independent sources and sum them up. The solution that you found is the same as when all the independent sources are in. So all the independent sources are in. This is the voltages of those two elements. And if I use the superposition theorem, I am going to remove these 3 independent sources and keep this one as it is. How I am going to remove these independent sources? These are independent current sources. Removing the independent current source means or deactivate independent current source to make them open circuit. So open circuit, open circuit, open circuit, they all has gone, and this is only one independent voltage source included. So after that calculation we've got that V1 here. In this one we keep this independent current source in and remove all or deactivate all the other independent sources. This independent voltage source, deactivate independent voltage source means the voltage became 0, that's short circuit. These are independent current sources, remove all these independent current sources or deactivate these independent current sources means open circuit, so they have gone. So only one this independent current source in and find out this voltage here. So if you repeat the same thing for the initial conditions related independent sources, this one and this one in here and here. So we found this and this. So that is our original circuit. So I divided this to 4 different circuits in here and find out the voltage between these terminals A and B. So you might consider that between these 2 terminals. So we are saying this voltage here between these 2 terminals, or this voltage, is equal V1, is the only one independent source included voltages that we calculated. So V1 prime, V1 double prime, plus V1 triple prime, that's this, plus V1 4 prime. So summation of this one, this one, this one and this one gives me when all these independent sources both at the same time included circuit voltage. So that voltage. That's what superposition tells us. So you might consider that that's not easy, isn't it? So you're going to analyze 4 circuits in order for the analysis of circuit like that. It seems a bit boring. But this theorem becomes useful if you use the multiplication of it. What I mean is this. Let's say a circuit given to you, last circuit, let's say assume this circuit. If I ask you what is the solution of the circuit if I replace these independent sources values to double the value. So that means let 5G and 5IG. So this theorem tells me whatever you found before you applied those is going to be multiplied with 5 for the solution of this circuit. Why I am saying so? So consider a simple form of it. If there is a circuit and there is an independent voltage source here, Vs. Now I am saying if I consider two vias connected in serial, and this part of the circuit is the same. So this is the same as this. So question is this: if I multiply this voltage by 2, that means your circuit is this, isn't it? This multiplied by 2, you get this 2 Vs. Now what I am saying is this: solution you found for this one plus the solution you found for this one, you're going to get the solution for this one, isn't it? For 2, isn't it? Let me repeat it. So maybe this one a bit confusing. Now this circuit solution, let's say all the elements, current and voltages, you found that. Now what would be the solution if I multiply this voltage by 2? That is 2 Vs. What would be the solution in here? I am saying whatever you found here is going to be multiplied by 2. Why is that? Because in my new circuit here, if I do the calculation by removing this one, I am going to find whatever I found here. That's one thing, isn't it? In this second time, according to superposition theorem, I am going to keep this dependent sources in and remove this one or deactivate this one. So this in, that's out, but it's going to be the same circuit like this, isn't it? So whatever you found previously for the red one is going to be found for this new one here. So these two solutions are going to be the same as this, because if you remove one of the independent source, you get this. So according to superposition theorem, addition of those two is 2 times Vs solution, isn't it? So for these elements, the elements within this circuit, these elements current and voltages multiplied by 2. Sorry, in this circuit, the elements current and voltages that you found multiplied by 2 gives you this circuit analysis result. So conclusion is that this is in practice from time to time called multiplication theorem. That means if you increase independent source, if you multiply the independent sources with K, a constant, all the elements current voltages will also be multiplied with K. That's the conclusion that we get out of the superposition theorem. It is true whether it is time domain or in frequency domain or in S domain. The only condition is the circuit must be a linear circuit, then these are all could be said. So that is the end of